In this video, we are discussing about the additional information and the full hypothesis test. The first part of the video is about testing a claim about a proportion. The goal is to conduct a formal hypothesis test of a claim about a population proportion P. Recall that the best point estimate for the proportion P is the P hat, which is a ratio of x over n, where x is the number of the individuals in the sample and n is the sample size. We are using two different ways for conducting a hypothesis test, which is the p-value method and the critical value method. Now, there's a few requirements before we can apply the test statistics to test for the population proportion. The first requirement is that we need to have a simple random sample. The second requirement is that the conditions for a binomial distribution are satisfied. So there should be a mixed number of independent trials having a constant probabilities, and each trial has two outcomes, which is success or failure, true or false, only two outcomes. And then lastly, the condition np0 is bigger than or equal to 5, and also nq0 is also bigger than or equal to 5 are both satisfied, so that the binomial distribution of the sample proportions can be approximated by a normal distribution with the mean to be np0 and the standard deviation is the square root of np0 q0. And recall that the q0 is just the complement of p0 or 1 minus p0. Okay, there are a few procedures for conducting the hypothesis testing. The first part A will focus on the p-value methods. The first step is to determine the null and the alternative hypothesis in one of the following three ways: two tails, left tails, or the right tails. So for the null hypothesis H0, we always see that there is the equality, the equal sign. So P equal P0. P0 is just the sum value of the population proportion that you assume that to be true in the beginning. So all the three cases we have P equal P0. And then for the two-tail case, we would say that the P value is different from P0. So this is a different side. Or the left tail, P is less than P0. Or the right tail, P is bigger than P0 for the alternative hypothesis. So if you look at the error, if it's pointing to the left, it is the left tail. If it's pointing to the right, it's the right tail. That's the way to remember. And again, the null hypothesis always includes the equal sign. The second step is to select a level of significant alpha. And this will depend on the seriousness of making a type 1 error. And the common choice is alpha equals 0.05, but normally the alpha is given for you in the problem. Now for the p-value methods, we are going to compute the test statistic, which is z0 equal p hat, the best point estimate, minus the p0, which is the sum value, over the square root of p0 q0 over n. Now we can use the table, the z-score table, to determine the p-value. For the two tails, we see that the sum of the area in the tails is the p-value. And because the normal curve is symmetric, if you can get just one area for z0, then you can multiply that by 2 to get the double area because they are symmetric. So just multiply by 2 with the area to get the total p-value for the two tails k. For the left tail, we just have to find the area to the left of z0, which is the p-value. And then for the right tail, it's the area to the right of the z0. The p-value is just the static ring area. And then we can also find those areas on the TI-83 or 84 by just using the normal CDF function. I'll show you that when we get to the problem. Now again, if the p-value is less than alpha, we reject the null hypothesis H0, and if p-value is bigger than alpha, we do not reject, or we fail to reject the null hypothesis. Part B, using the critical value methods. Now repeat the same steps 1, 2, 3. 1, 2, 3. We are using the same step, but now instead of computing the p-value, we use the table, the z-score table, to find the critical value instead of the p-value. Okay, so again we have three cases: the two-tail, the left tail, and the right tail. For the two tails, we would need to find what is the z alpha over 2, the critical value, and minus z alpha over 2. And then the right area is the critical region, the same thing to the left area. And then the same thing to here. The left tail, we have the left critical region, and the right tail, we have the right critical region. Okay, so we have to compare the critical value z alpha over 2 for the two tails, or z alpha, with the test statistic. Now, if the z0 is less than or the minus z alpha over 2 or bigger than z alpha over 2, then we reject the null hypothesis. In other words, if your z0 is inside the critical region of the three cases, then we reject the null hypothesis. And again, when checking the requirement np0 is bigger than 5 or nq0 is bigger than 5 for small sample size, it usually won't pass the conditions, and we need to use the binomial distribution instead of the normal distribution approximation. Okay, let's go over the very first example that we have here. The Genetics and the IVF Institute conducted a clinical trial of the YSORT method, designed to increase the probability of conceiving a boy. As of this writing, 291 babies were born to parents using the Y-short method, and then 238 of them were boys. Use a 0.01 significant level to test the claim that the Y-short method is effective in increasing the likelihood that the baby will be a boy. Okay, so first thing again, let's try to use the p-value methods. You have to check the requirements. We have 291 babies were born, so that is the sample size n. Now this is a random experiment, so the simple random sample is okay. This is again a binomial distribution. We have two outcomes only, the boy or the girl. And then we check for the inequality. np0 is bigger than 5, and n minus p0 is also bigger than 5. Let's check that. Okay. The original claim. Now, the Y-short method is effective. We are checking to see if the Y-short method here is effective or not. Now, if this method is effective, it should mean that the proportion of getting the boy will be bigger than 50% or 0.5, right? So if this one is effective, then you assume that the proportion should be bigger than 50% of getting the boy. Proportion of getting the boy. And 50% is what? 50% is 0.05, or P is bigger than 0.5, 50%. Now, because the inequality P bigger than 0.5 does not contain the equality. Therefore, this is the alternative hypothesis. Remember, only the one that has the equal sign, that would be the null hypothesis. This one is bigger than psi, which is the H0 or the alternative hypothesis. And therefore, you just have to replace the bigger than psi with the equal sign and make that to be a hypothesis for the null hypothesis. And then the value of P0 is 0.5 here. And therefore, you multiply 0.5 to n 291, it should be bigger than 5. So that all the requirement checks are okay. Alright, now, because this one is pointing to the right, it is a right tail test, and the alpha is 0.01 significant level. And then we use the what? The point estimate formula before. P hat is equal x over n. X here is 239. Because the value for the problem here, we have 235 of them was a boy. So x is the subject. So x, 239 out of 291 of the sample size. And that's the ratio, 0.8121. And then you apply the z statistic, the z test. And we have everything. We have p hat, we have p naught, we have n, we have q naught. Then we can find z naught. Z naught is 10.952. And again, this is the right tail test. So you are looking for the area to the right of this z statistic. Now, on the TI-84 or 83, we can find the right area right here by using the normal CDF function. If you use that function, so let's try that. We go to second var to get to distribution. We go to normal CDF. Now the lower bound is your z naught or 10.952. The upper bound we go all the way to the right, so I just have to enter a very large value like 10.9999 or 10 to the 99 power, as long as you put a very large value. And then the mean is 0, the standard deviation is 1 because this is the standard normal curve. And then hit the enter, and that should give you what the value, the p value. Okay, the p value. And this one is extremely small, right, to the power of minus 28. So 0.0000028 of 0 is very small. So this value is of course is less than the significant level alpha, 0.01, and it's less than alpha. We then reject the null hypothesis. So we reject the h naught. Now for the critical value, after we find the test statistic, we're gonna find the critical value instead of the p value. And then from the previous chapter, we know that because we are given the alpha to be 0.01, and this is the right tail, so this area corresponds to the right area of the z alpha or the critical value. Now we are given the area and you want to look for that z-score, so you have to figure out what is the left area. The left area is 1 minus 0.01 because everything is 1, and therefore you can find the left area by subtracting 0.01 from 1, and we use the function inverse num and then input the area to the left to give me this z-score. Or you can use the second var inverse num function on the TI-84, and you should get that to be 2.33, this z value. So z alpha equal 2.33. However, your test statistic z naught is 10.952. So it's all the way after 2.33 is all the way over here. And therefore, it is inside the critical region. So anything inside the critical region, that you saw before, anything is inside the critical region, we reject the null hypothesis. And in this case, because z naught is bigger than z alpha, this should be z alpha, then we reject the null hypothesis. Okay, so you can see that here the p-value and the critical value methods, they both give the same answer, which is rejecting the null hypothesis. Or the conclusion is that there is sufficient evidence to support the claim that the Weierstrass method is effective in increasing the likelihood that a baby will be a boy. It is effective because we reject the null hypothesis. Therefore, the proportion is bigger than 0.5 or more than 50% will be a boy, or the method is effective. And we can also use the TI-83 or 84 to do the whole testing for the p-value. Now let's try that. We will use the one proportion z-test command to perform a z-test to compare a population proportion to a hypothesis value. Now this test is valid for sufficiently large sample values, so it's only valid when np0 is bigger than 5 and nq0 is bigger than 5. Okay, so now let's try that. You're gonna hit the start button, and then you're gonna go to right arrow to the test, and then move down to one proportion z test. We are performing a hypothesis testing, so make sure you pick the test. And this is the z statistic, the z test, so make sure you pick the z for proportion. So now hit enter. Alright, so remember your p0 we got earlier here. Remember p0, it is 0.5. p0 is here. So input 0.5, and then your x is the subject, and that is the x value we got earlier, 239. The sample size 291. Now we are looking for the right tail test, and therefore you want to pick the right tail, which is the third option, and then hit the enter key. Make sure you pick the correct right tail test, and then now you want to click calculate here, and then hit enter, and now you get everything here. Your z is the test statistic, z test, your p value, and your p hat. So again, p value is closing to 3 times 10 to the negative 28. So it's very small. It's less than the alpha level or significant level, and therefore we reject the null hypothesis. So the TI-84 also help you to get to the same conclusion. Okay, let's go over another example. In 2006, 10.5% of all the live births in the United States was to mothers under 20 years of age. A sociologist claims that this percentage is decreasing. Then she conducts a simple random sample of 34 births and finds that 3 of them were to be the mothers less than 20 years of age. Now, that's a sociologist claim at the level alpha of 0.01 level of significance. Okay, so we are given the percentage, the proportion of all the live births in the United States was to the mothers under 20 years of age, and therefore this value is the assumed value, and that is the p0 value. So that is the p0 value. And the sample size in this case, she conducts a simple random sample of 34. So n is 34. And then we only find out that 3 of them was to be the mother less than 20 years of age. So the number of the subject x is 3. Now, we will use the p-value approach in this example only, so that we can also use the TI-84 to confirm the answer. Again, first thing is you have to check the 3 requirements. First, simple random sample. Yes, because she conducts this one has a simple random sample of 34 births. So yes, this is a binomial distribution. That is also correct. So we either have the models to be less than 20 years of age, or we have a higher value, right? And then the last one is that you are checking for the normal approximation to the binomial. So if n times p naught is bigger than 5 and n times q naught is bigger than 5, then we are all good. N is 34, p naught is 0.105 in decimal places. You multiply that together, it's only 3.57. This is less than 5, and therefore we don't meet the third requirement of the normal approximation to the binomial. And therefore you cannot use the normal approximation to the binomial distribution. Now let's set up the hypothesis claims. The null hypothesis has the equal sign. So this is the proportion case with the percentage. So P equal P naught. So P equal P naught. And you are looking to see if it is less than 20 years of age, or is you are looking for the claim that this percentage is decreasing. That means it is less than the assumed value, or P less than 0.105 here. Alright, so now we have x equal 3 successes in the total of 34 trials. Now, the p-value is equal to what? Is equal to p of x less than or equal to 3 in this case, because 3 of them was to be the models of less than 20 years of age. And again, we cannot use the normal approximation to the binomial distribution, and therefore you have to use the regular binomial distribution. And to find the p-value or the area or anything less than or equal to 3, we can use the cumulative distribution function of the binomial on a TR-84 or 83. Let's try that. So open the TR-84. We're gonna go to the second verse. In this case, this is the binomial. So we are using the second option. No, sorry, the binomial, not normal. Binomial CDF. Recall that from the lattice sample, we use the normal CDF because the requirement n p naught is bigger than 5. But now it's less than 5, so we have to apply the binomial CDF. Now the trial, in this case, we have the total of 34 for the sample size, so there are 34 trials. The p value is the assumed value. We assume it to be 0.105. That is the p naught value, the assumed value. And then lastly, the x value, we are looking for x to be less than or equal to 3. And that's 3. And then let's paste everything here. And it should give you 0.5148. And that is the value of the p-value. And we know that alpha is 0.01, and our value p-value is 0.5. This is much bigger than 0.01, so it's bigger than bigger than alpha. We do not reject the alpha, the null hypothesis. So we do not reject the null hypothesis, and therefore we do not support this. So there is insufficient evidence to conclude that the percentage of the live birth in the US to the mothers under the age of 20 was decreasing in 2006. We don't have enough evidence to support the alternative hypothesis because we did not reject this, and therefore we cannot make the conclusion about the statement here that is said that it was decreasing. We cannot confirm that. Insufficient evidence. Okay, so that is the example about the testing a proportion using the binomial distribution when the normal approximation is not allowed. In the next part 2 here, we are going to test a claim about a mean after we learn about the proportion. Now the goal is to conduct a formal hypothesis test of a claim about a population mean mu. Now recall that the best point estimate of the population mean is the x bar, which is the sample mean. So again, there are two methods that we normally use to conduct a hypothesis test about a population proportion or the mean in this section or in this second part here. We will focus on the p-value and the critical value methods. Now, for the mean, there are always two cases. The first case is when we don't know anything about the standard deviation of the population. And then the other case is when we do know the value of the population standard deviation sigma. Okay, so let's quickly review about the requirements and the sampling distribution that we are using for the mean. Now, for the case that we don't know anything about the sigma or the population standard deviation, then the sampling that we are using to do the testing is the student t distributions, and the requirements that we need to check is that make sure that it is a simple random sample and the population is normal. If not, then make sure that the sample size is bigger than 30. And then this is just a test statistic that we saw earlier. T naught is x bar minus mu naught over s over the square root of n. And s here, the small letter s, is just a sample standard deviation. And then for the case that when we do know the value of sigma, then we just have to use the normal or the z distribution. And again, we need to have the simple random sample and normally distributed population. If the population is not normally distributed, then make sure that the sample size is bigger than 30. And then we just have to apply the z test statistic. Z naught equal x bar minus mu naught over sigma divided by the square root of n. And sigma again is just the standard deviation of the populations. And again, the x bar is sample mean, mu naught is the population mean. There are some value, and n is just the sample size. Now sometimes the sample size of 15 to 30 are sufficient if the population has a distribution that is not far away from the normal. Okay, the first part will focus on the p-value methods. So there are a few steps for the p-value methods as similar to what we saw from the proportion case. The first step, as always, we have to determine the null and the alternative hypothesis in one of the following three ways. Again, we have the two tails, the left tail, and the right tail. For the null hypothesis, we always include the equal sign. So we assume that the population mean is equal to some assumption, at some value, mu naught, for all the three cases. For the two tails, then we assume that the alternative hypothesis h1 is different from the assumed value. For the left tail, we assume that it's less than the assumed value, and for the right tail, we assume that it's bigger than the assumed values. And again, for the left tail, we see that the arrow is pointing to the left, and for the right tail, we see that the arrow is pointing to the right. And the null hypothesis always include the equal sign here, here, and here. And then we select a level of significant alpha, which is a type 1 error. And it will depend on the seriousness of making the type 1 error. Now, the type 1 error is when we reject the null hypothesis when it is actually true. And the common choice for the alpha is 0.05. And this is normally given for you in the problem. And then for the p-value methods, we are going to compute the test statistic T0. Now, when we are using the T statistic, we have to apply the degree of freedom, and there is always n-1 number degree of freedom. And if we use the z statistic, then we know that the sigma, the standard deviation, is given for you. And then you can also use the table A2, A3 to determine the p-value, or you can also use the TI-84 or 83. Now for the two-tail test, again, because the graph is symmetric, all you have to do is you find the area of one side, one tail, and then multiply that by 2. The p-value is just a sum of the area in the tails. Again, it's similar to the proportion case. And then for the left tail, it is just the area of the left tail, and then the right tail is just the area of the right tail. Now for the critical value methods, we will consider that in the next example. But it's similar to the proportion. And also for the z test, again, the graph is also symmetric comparing to the t test. So all we have to do now is we just have to find the area of one tail, and then double it when you are solving the two-tail case. The p-value, again, it is just the shaded green area, and we can find that using the t-CDF function for the student t, or the normal CDF function on the TI-83, 84 for the z distribution. Now, if the p-value is less than alpha, alpha is the level of significance, then we reject the null hypothesis. And if it is bigger than alpha, then we do not reject the null hypothesis. Now, for the critical value methods, the second part of this sections, we keep the same step 1 to 3 as we saw above. However, we find the critical value instead of the p-value. Now, if it is a normal z, then we have again 3 cases: the two tail, the left tail, and the right tail. Z alpha and minus z alpha are for the left and the right tail, and then z alpha over 2 is for the two tails, because we have to split it up into 2 equal area. And as long as your z0 is inside the critical region, we reject the null hypothesis. And then for the student t, then it's the same thing. We have 3 cases, and as long as the t0 is inside the critical region, we then reject the null hypothesis. Okay, there's a note here. When working with a small sample size n less than 30, we must verify that the sample data is coming from a normally distributed population. This is very important, and we can do this by using a normal probability plot or the normal quantile plot. And if the data adheres with a linear relationship or a straight line, then we are good. Okay, make sure that we can get a linear relationship between the x and the y's values. Then it indicates that your data is coming from a normally distributed population. And in order to check for the normal probability plot, we use the second start plot. Then we use the last option here, and then just plot the data that is given for you. We will go over that example in the next few problems. Alright, so let's go over this for the example here. We have a simple random sample of the weight of 19 real M&M has a mean of 0.8635 gram and a standard deviation of 0.0570 gram. use a 0.05 significant level to test the claim that the mean weight for all the real M&M is equal to 0.8535 gram, which is the mean weight required so that the M&M have the weight printed on the package label. Do the real M&Ms appear to have the weights consistent with the package label? So in this case, we are given the sample size of 19N, and it's said that this sample has the mean X bar with this value, and also the sample standard deviation, the small s. Now, we don't have anything about the population standard deviation, and therefore sigma is unknown. And if that is the case, we have to use the student t distribution. So we know n, we know alpha, x bar, s, and we are testing for the claim whether that the mean weight is equal to this value or not. So this value here is the mu naught value. And again, anything with the equal sign, we put that for the null hypothesis. And if it's not equal, then it should be different. So the alternative hypothesis is the two tails, or the different size. So there are two requirements that we have to check. This is a simple random sample. It's given here. However, the second requirement, 19 for sample size is less than 30. So if it is less than 30, we need to make sure that if the population is normally distributed or not. And this is the data that we are given, the weights for all the M&M means, the 19 M&Ms mean. Now, we have to check for the normal quantile plot. So what we do now is we go to TI 83 or 84. You're gonna hit start, edit, and then using the list L1, you are going to enter all the value or the number into the list L1. So after we have all the values input here, then you can check for the normal quantile plot, and we can do that by using the start plot. So let's go ahead and follow this direction here. We're gonna go to second start plot, and then let's turn on the plot number 1 so that we can use it. Alright, so I'm gonna enter, make sure you turn it on, and then you're gonna choose the last option, which is the normal probability plot. So click that, and we use the data that we enter from the list L1, and the data axis is your x-axis, and then you're gonna enter. So make sure you choose all the value, and then now you're gonna go to the zoom, and then choose the option number 9, zoom start, so that it will plot you the normal probability plot. And we see that the normal probability plot on the normal quantile plot here is exhibits a straight line pattern. So it seems like the data is coming from a normally distributed population. So even if your sample size is less than 30, we are still okay for the requirements. Okay, so now it is the two tails test. Again, this value is your mu naught. So I apply the student t, the t statistic. We got x bar, we got mu naught here, the sample standard deviation, and then the n, the sample size. So you got this value 0.765. And then because this is the two tails, the difference is the two tail case, then your t naught is 0.765 here. You just have to find one area and then just double it, alright, because this is symmetric, to get the whole p-value. Now you can use the function tcdf. Okay, to find the area of the right tail. Now let's try that. Second, vars to get to the distribution. And then TCDF is the option number 6. Alright, so the lower bound is here. The test statistic, so that's going to be 0.765. The upper, you want all the way to the right, to infinity. So we can just use a very large value, like 10 to the power of 99, extremely large value. And then the degree of freedom is n minus 1. We know that we have the degree of freedom is n minus 1. Because 19 is the sample size, so 19 minus 1 or 18. So let's place everything into the TCDF function. So this is just the area of one tail on the right only. So we need to multiply by 2 because you want the double of that. 0.454 is the answer that you should get. And of course, this value is bigger than the alpha or the level of significance. And because this is bigger than alpha, we do not reject the null hypothesis. If we do not reject the null hypothesis, that means we do not reject the mean is equal to 0.8535. We do not reject that statement. And if we do not reject, then we say that there is not sufficient evidence to warrant the rejection of the claim that the mean weight of all the real M&Ms is equal to 0.8535 gram. Therefore, the real M&M do appear to have the weight consistent with the package label, because the package labels is saying that the mean weight is equal to 0.8535. That is what is printed on the package label. And because we do not reject that, so that means we may conclude that it does appear that it is consistent with what is given on the package label. The last topic is how do we use the TI-84 to find the p-value. It's just like the proportion test. Now, because we are doing the t distribution, so you want to choose the t-test. Okay, so first thing is you're gonna go to start, go to the test. Now we are looking for the t-test. All right, t-test. Okay, so we store the data from the list L1, so you want to keep the option of data, and make sure that you choose the list L1 because we store everything on the list L1, the 19 values of the weights. Okay, just go back to the test, t-test. All right, so your assumption value is 0.8535. That is the mu naught value. This is the two-tail case. So this is you want to select the different side, right? This is your alternative hypothesis right here, two-tails case. Okay, and then hit calculate. Then you get your t-test. Your t-test displays everything that you need in this problem. This value, the t, is your test statistic, and the small p here is your p-value, which is exactly what we got here, 0.454. So if you can use the TI-84, you're gonna get the answer right away. There's no need to go over this step or even find this t naught value. Everything will display for you instantly if you use the TI-84 for the testing. Lastly, you can also chart the graph here. Right, you can chart the distribution here. So just by going to start again, go to test again, the t-test, And instead of calculate, you're gonna select the draw and then hit the enter. It will draw the curve, the distribution. This is the left tail and this is the right tail, and I give you the t statistic. T equals 7672, which is this value right here. And because this is the positive value, we know that this is the t0 value of the right tail, and the p-value is also given, which is consistent here. So it's a nice way to display the graph and the distribution.